All right, that should be it. Well, hello everyone. My name's Diego Ferrer, and today we're gonna talk about Celestia. Specifically, I'm gonna do more of a deep dive, or usually or deeper than what we usually do for these kind of presentations. That's why I titled it from NMTs to DAS. We'll talk about what that stands for and sort of like um, how it's the sort of like underlying data structures as well as the underlying mechanisms that allow Celestia to do what it does, right? And also like go a little bit into like uh, the very beginning. So Celestia, what were the ideas and concepts behind it, and it's gonna be kind of it's gonna be kind of a sort of like simplified walkthrough of um, the white paper that essentially marks the beginning of like Celestia, right? So about myself, I have a bachelor's of science in computer science from the University of Florida. I was previously at a Web3 slash NFT startup called Tessera, where I was a smart contract developer full time for almost a year, essentially just writing Solidity smart contracts, doing a lot of not only development but also testing. And I believe the one of the highlights there is that we were one of the first like users of Foundry, and the very early like libraries that surrounded Foundry for testing and deployment and production and all that stuff. I was also a software engineer intern at Microsoft before that. And before that, I was a blockchain developer intern at Quantum. That's kind of how I got started in the space professionally. Um, and most recently, well, I joined Celestia Labs, which is the core contributor or one of the core contributors to Celestia, the protocol. And I joined as a solutions engineer in January of this year. So the Celestia origins. So everything started when Dr. Mustafa Al-Wassam posted the Lazy Ledger paper. I believe that was back in 2019. The title of the paper being a distributed data availability ledger with client-side smart contracts. I left the, well, you can't click on the link, but you can type it in your browser and get a PDF copy of it, or you can search for the title of the paper and you should be able to find it if you want to fully read through it as well as read up on the references. So why Lazy Ledger, right? Like the original design and concept that underpins like all of Celestia. Well, so in to kind of go over the introduction of the paper, in blockchains like Bitcoin and Ethereum, the validity of blocks that are proposed by block producers are determined by like whether it's the turn of a given block producer to produce a block, right? Obviously, in Bitcoin, this turn is determined by like proof of work, and on Ethereum is nowadays proof of stake. And then also the validity of the block is determined based on whether the transactions inside of the block are valid according to some state machine. We say state machine just to represent like any form of state transition, right? So in the case of Bitcoin, is very simple, right? It's just the opcodes that you can call using Bitcoin script, nothing super fancy. And then in the case of Ethereum, right, to verify the validity of some block, you have to verify the validity of the instructions that were executed on the EVM, right? You want to make sure that the outputs are correct, right? Given a set of inputs and all that stuff. Then the paper goes on to talk about the fact that the scalability issues that have plagued decentralized blockchains can be attributed to the fact that in order to run a node that validates a blockchain, the node must also download, process, and validate every transaction included in the chain, right? So if we start thinking about it in the context of the blockchains that we previously mentioned, it's very obvious why the hardware requirements to verify the Bitcoin blockchain are so much lighter than to verify, say, Ethereum, and it makes it also clear why the hardware requirements to verify a blockchain like Solana are so much more bigger / beefier, right? Like you need high-end great hardware to be able to actually verify or follow the tip of the chain for something like Solana, right? And I think in general, this part of the paper really speaks to something that if you've been around for the past, I would say 3-4 years, something that's become obvious is that the bottleneck of all these blockchains, right, ends up being it's not execution, right? Because ultimately, you can switch out the virtual machine, you can do all this different stuff, but if you end up going too much on one side of things, right, like something like Solana, you kind of lose on verifiability, and in some sense you lose in decentralization, right? And ultimately, it's also I think what this part also makes apparent is that you can't just simply make blocks bigger, right? There's been many alternative layer ones that use the EVM as the state machine, and these alternative layer ones have like higher gas limits than Ethereum, and even though the validators run beefier hardware and these blockchains don't care as much about the validator count or decentralization, they ultimately end up having the same problems, right? The same sort of like gas issues or issues of like essentially having bloated mempools, right? Too many people trying to access the same stuff at the same time. And if you were trying to verify one of these like blockchains, you would have to essentially your job becomes harder, right? Because now you have to verify the validity of even more transactions, right? In a single threaded like environment. So obviously, over time, as we all know, scalability efforts emerged with on-chain methods such as sharding, right? Which I'm not going to talk about sharding, but essentially, right, you make these like separate like subsets of consensus that verify like different parts of a block, etc. Like essentially do like shard execution. I believe the only, I'm not going to say the only, but a famous example here would be something like Near, right? And in the case of blockchains like Ethereum or Bitcoin, ultimately people decided on doing things that are off-chain, right? Like these off-chain methods all started with things like state channels and Plasma, and have now evolved to rollups, right? Which are like the talk of the town nowadays. So continuing on from the sort of like lazy ledger paper introduction, the design that Dr. Mustafa, or from now on, let's just say Mustafa, proposed, it's essentially a blockchain that's optimized for ordering and guaranteeing the availability of transaction data, right? So if you read up on on the paper and also sort of like on distributed systems and consensus, the core function of a consensus system for distributed ledger is to order transactions and ensure the availability and ensure their availability. Consensus participants do not necessarily need to be concerned with the contents of those transactions, right? Shifting the responsibility of execution and transaction validation to the app clients, in most cases rollups, or well, in most cases these apps are rollups, interested on the specific transaction data. It's like essentially one of the things that makes like this design different. If you think about it, if I have an application on Ethereum and somebody else on this call also has an application on Ethereum, and somebody's trying to run a node to verify the network, they have to verify the contents of the transactions for my application and the other applications on the chain, right? But with the sort of like proposed design of the Lazy Ledger paper, this responsibility is like shifted individually, right? It's the same concept, really as like rollups, where if I run a rollup, I only care about verifying that the transaction data that I posted on Ethereum, say, is available, right? And I am responsible for ensuring the validity of that transaction, but I don't necessarily care about the validity of the transaction data for another rollup, right? Like Optimism only cares about the inclusion of its data and the validity of its data, but it doesn't have to care about the inclusion or the validity of the data of, say, Arbitrum, right? So by doing this, you essentially reduce the block verification to data availability verification, which can be achieved probabilistically with sublinear complexity without downloading the whole block. The amount of resources required to reach consensus can thus be minimized, as transaction validity rules can be decoupled from consensus rules, right? So what essentially, we'll talk about the data availability verification and all that stuff later on, data availability sampling. But essentially, the Celestia state transition function is like a very simple one. It essentially just takes data, does a two-dimensional Solomon read encoding, and then essentially like produces fraud proofs, and shares it with like peers to, so people can verify that things were correctly encoded. And that's pretty much it, right? So if I supply my data, or if I submit my data to Celestia and everyone else on this call submits their data to Celestia, right, for their own specific rollups, the Celestia validators and people that are running Celestia-like clients don't need to they don't need to run the state transition function for each one of our rollups in order to verify that the data was made available for all of them, right? And it also has the benefit that I only need to verify that the data from my rollup was made available. Then that kind of brings us into this idea of like modular and monolithic chains, right? I got this image from the slides that we typically use for more like basic presentations on Celestia. So going off of what I just mentioned about the Lazy Ledger paper, the idea of separating the verification or the validity of the transactions of your application essentially evolved into the idea of like having modular blockchains, right? So when you have something that's monolithic like Bitcoin or Ethereum, both the execution of your transactions, right, like the validity of those things that you're asking the network to execute, are tightly coupled with like consensus and data availability of the network, as well as like the settlement assurances that you get. When you decouple these things, you have things like Celestia that are solely focused on consensus and data availability, and shift the responsibility, if not the task of transaction validity, to the rollups and applications on top of it, right? So in the same way that Ethereum has a rollup-centric roadmap for essentially scaling itself by shifting the responsibility, let's say, upwards. Celestia kind of thought about that as the best approach period from the beginning, and thus shifts the responsibility of execution and settlement to all the layers that are above it. So what makes Celestia different, right, from, say, traditional blockchains and whatnot? So nodes that need to validate the Celestia chain do not need to validate the contents of the blocks, right? So if I am running a light client for Celestia, I don't need to, again, like verify that. I don't have to like take the data, serialize it into different transaction formats, verify, run them through multiple virtual machines and verify that all those are like valid. I just need to make sure that there is a bunch of data that was correctly encoded, and I can go about my day, right? As we mentioned, it removes the bottleneck where nodes need to verify everyone else's transactions, and also reduces the problem of validating the blockchain to simply verifying that the contents are available, right? That, I think that's a very key important part of like Celestia and sort of like why we put so much focus on end user verifiability and allowing people to run light clients. And ultimately, users can meaningfully access the data needed to apply the state transitions to their apps, right? So I'm gonna go over like on that a little bit later as to what that means, like what does it mean to meaningfully access data needed. But yeah, so now we're gonna talk about sampling-based data availability, right? So the data availability problem asks how a client such as a light client, which only downloads block headers but not the corresponding block data, example, or in other words, the list of transactions, can satisfy itself that the block data is not being withheld by the producer of the block, a miner, block producer, or miner, or somebody who's the current leader in some proof of stake scheme, right? And that the full node and that the full data is indeed available to the network, right? So the proposed solution for this, in the case of the Lazy Ledger paper and what Celestia is currently using, is essentially a combination of erasure coding and random sampling, right? The paper goes more on detail. Well, the Lazy Ledger paper it's not going to tell you exactly like oh, what's erasure coding and whatnot, but it leaves you with the necessary like links for you if you want to read up more on erasure coding. But it explains the scheme that's used in Celestia, the reasons why, and whatnot, right? So I put this image on the slide to kind of give an idea of like what it means to have sampling-based data availability, right? So like clients are able to sample small chunks of data in order to be able to know that the rest of the block data was available or was made available. So what is Celestia's like erasure coding scheme? So Mustafa proposed a two-dimensional Reed-Solomon encoding scheme. So the reason for that is that if you do a single dimension or just a basic Reed-Solomon scheme, you do have the advantage that you only need to keep like a single Merkle root for a single Merkle tree. However, because the block producer can like incorrectly compute the erasure code of the Merkle tree, thus making the block data unrecoverable, meaning nobody can recover the data if you don't correctly apply the erasure coding to the data. It is necessary to allow clients to receive like fraud proofs or alerts from full nodes that lets people know that the erasure code was done incorrectly, right? Then that alerts the client to download the block data and recompute the erasure code and verify that it does not match the Merkle root, right? essentially, if you do a basic Reed-Solomon scheme, everything works great in the happy path, but in the usual / common not so happy path where somebody is trying to like do something bad, or not necessarily do something bad, where somebody makes a mistake and they incorrectly encode the data, then that would require like clients to have to download the entire block data when things are not correctly encoded, right? The problem with that is that kind of like defeats the purpose of everything. So in order to prevent clients from needing to download the entire block of data, we use two-dimensional erasure coding, right? That makes it so that the fraud proofs only need to happen to a specific axis, as only one row or column needs to be downloaded to prove that the erasure code is incorrectly computed, right? That's sadly I don't have like a good visualization of like what that entails and what does it mean to do two-dimensional Solomon Reed-Solomon coding. But essentially, because of two-dimensional Reed-Solomon encoding, we don't have to download the full block of data in case there's been fraud. You can essentially just verify the incorrect rows or columns, and essentially can check whether like or you can check whether the whole block was like done correctly or not, right? Without having to download the full block of data again. In the case where you want to check, right, that fraud has been committed or wrong encoding has been done. Now, going back to what I said about like efficiently like retrieving data or meaningfully retrieving data, and sort of like giving you all an idea on like how Celestia stores its data. So for background context, in case you need a refresher, blockchains like Bitcoin and Ethereum use Merkle trees, right? Ethereum specifically uses Merkle tree, right? So they use these like Merkle trees to store the data, right? Now, Celestia uses like a flavored version of that called a namespace Merkle tree, right? Here's a good image I found from the blog post from 0x Writing Coffee, who does a lot of good writing on different stuff. And I just like this image, so I put it here. So before I go into the next slide and talk more about like namespace Merkle trees, right? Obviously they share similarities with regular Merkle trees. Like obviously there's a root to this like Merkle tree, which is usually included in the block header, right? And in Ethereum, you have the root of the Merkle tree for the state of the block included in the block header. And in the case of Celestia, you have the root of the namespace Merkle tree. And obviously as a tree, you have nodes, you have leaves, etc. And I think the thing to highlight here is like that bottom part of the tree called where you can see like the namespaces. So a namespace is essentially you can think about it as like a subsection or an area of the leaves of the tree where you essentially have like some data, right? That's obvious, right? But what that means is that if I commit to namespace 1, my data will only be in the leaves that make up namespace 1. There won't be like my data won't be randomly located in like namespace 2 or 3. And this kind of gets us into like talking more about NMTs and what they are. So as I mentioned before, they're a variant of Merkle trees, but NMTs specifically organize the data into a hierarchical structure. in which the hierarchy is defined by the namespaces. And this allows like efficient verification of individual or separate pieces of data that you request. So if you want to fetch data or verify data for specific pieces of data, you only need to get the nodes and leaves that compromise your namespace to verify, say, that some data is inside of my namespace, not my namespace, because namespace they're not reserved, right? Anyone can put data on a namespace, but this essentially makes it easier for record keeping. If you think about it, right, like my blockchain knows the data that it has, or sorry, my rollup knows the data that it has created, and by publishing it to Celestia to the same namespace forever, I can simply just query the namespace of the Merkle tree, which is essentially just leaves, and I don't have to query or verify inclusion by having to construct a full tree or even like adjacent namespaces. I only need to care about the subtree that makes up my namespace, if that makes sense. And that's obviously a huge advantage, right? For not only for like the software side of things when it comes to like running a light node and also storage, but it's also very helpful when you want to do on-chain proofs of data inclusion, right? Like if I am an application or some sort of software that say lives on Ethereum or some other EVM chain or whatever, and I happen to post my data to Celestia because it's cheaper than using Ethereum cold data, I still want to somehow verify whether my data was like included on Celestia or not in a cheap and efficient manner. And namespace Merkle trees allow us to essentially verify data on chain by essentially like hashing your data. You know, it's the same way you would do a Merkle tree storage proof. Like you would kind of do something very similar by hashing your data and essentially making an inclusion proof on chain for only the namespace and node that you're looking for without having to like construct like a larger tree, right? So it's there's that benefit. The other thing is that, for example, you can have nodes on the network that only keep track of like certain namespaces. So in the case of, say, a rollup on top of Celestia, you can essentially run a client or partial client. Well, partial client is not a great name, but let's say it's a like partial storage or I forgot what the proper name is, but essentially instead of having to run a storage node for the data of like the entire network, you can run a node that only keeps track of like the data in the namespace that you define, right? That you give it. So if I say I only care about namespace 2 because that's where my rollup data lives, then my node only needs to keep track of namespace 2 and it doesn't have to keep track of namespace 1, 3, 4, etc. So a better graphic of namespace Merkle trees and what it means to fetch the data. So if you look at the bottom part in namespace 2, this gives you sort of like a good idea of like how you would prove or fetch, or well, not only just fetch data from the namespace Merkle tree, but also how you would prove inclusion. So for namespace 2, let's say you want to get data chunks 4 and 5, which is D4 and D5. You would need to provide the namespace Merkle tree with node 3, 4, 5, and 6, and data chunks 3 and 6. So you don't have to provide the nodes or leaves that are not part of the that are not parents to your leaf nodes, right? So for example, like node 8, 0, 1, 2, and 7 can essentially like be disregarded because they don't form, they're not necessary to sort of like go down the tree to go to your leaves. And yeah, obviously this is like a very basic example of a small tree, but it gets more significant like the larger the tree. You get to see more of the reasons why it's like why namespace Merkle trees are like a good construct for essentially like a data availability focused network. And
Hello.
yeah, lastly, yeah.
Hey, I just have probably a some question about the name Merkle tree, the namespace Merkle tree.
Yeah,
Can we
yeah.
go to the slides?
Yeah, I can go over it in a second. I actually this is my last slide.
Yeah, sure.
So yeah, like, and lastly to kind of like finish it up, things that you build on Celestia. So you can build anything really. It's like one of our slogans is like build whatever, because you can literally build anything since you only use Celestia for making your data available, like as a form of like data publication or verifiable data publication. But more specifically, people build like sovereign rollups, right? Like these rollups are like pessimistic if they don't have a proof system, optimistic if they have fraud proofs, and CK if they're CK rollups, right? And you can also build Ethereum L2s or L3s that use Celestia for DA. And yeah, I can go over any questions now and try to go back on my slides on my phone. There we go. So namespace Merkle tree, I believe the question was. Let me know if you want this diagram or this one.
Yeah. So I probably have some question. I think there's another diagram showing the n some number and some. Yeah. I'm just curious, like, what are the definition of each one, like n14, comma and 1, 2, 3. That what does that mean, like in this presentation?
Yeah, so this image I pulled straight out of the Celestia docs for the namespace Merkle tree. So the n the ends signify like node, right? So node 14 is like the root of the namespace Merkle tree, and then every node underneath it is like and 12 and 13, right? They're nodes 12 and 13. So it's like the number of the node. Essentially, if you look at it from the bottom left, you can kind of see how they're numbered, right? Like it goes from the bottom left and keeps on going from left to right until it reaches the top. That's how they're numbered. It's more for like this like visualization purposes.
I see.
And to be fair, I don't know who made this diagram. I just know it's in the docs. But the other parts of the diagram, let me see. The bottom parts, like the namespaces, D means like data chunk. So like the data that lives under a leaf. So you have all the different data chunks. And I'm trying to figure out the other parts. So in the namespace Merkle tree, the leaves are ordered by the namespace IDs or namespace identifiers. And there is a modification where the hash function, in this case SHA-256, every node in the tree includes the range of namespaces of all its descendants, right? So if you look at the root of the of in this diagram, like node 14 all the way at the top, when it says 1, 2, 3, it means that the the root, right, contains the range of all the namespaces on the tree, which in this case is namespace 1, 2, and 3. And if you look at its descendants, node 12 possesses data from that ranges from namespace 1 to namespace 2, and then node 13 possesses data or possesses nodes and leaves that belong to namespace 2 and 3, right? That's like that's why once you get like at the bottom of the tree, you can see how the ranges are only for that namespace, right? So in namespace 1, every leaf only ranges from namespace 1 to namespace 1 because they only belong to, like, they have no descendants and they only belong to namespace 1, right?
I see.
Yeah. And then H is a hash of the descendants, or you hash the direct descendants of like each node. So yeah.
Yeah, okay, great. Yeah, because like at first time when I read N14, I was confused whether it's a namespace or just a node ID. But yeah, thanks for pointing out this is a unique ID of this node.
Yeah, no problem. But to be quite honest, the first time I went through the documentation, I had the same confusion. I thought that the N standard for namespace. I've had similar issues. I had similar issues at the very beginning. But this is good feedback. I might tell someone that we should make this clearer because it took me a minute to remember exactly what everything here is, right? But yeah.
Great. Another question, like for the namespace, that is ordered from 1 to 3, right? But in reality, that is kind of like random ID, or how should it look like? Kind of like
Yeah, it is random, right? So this root, or well, it's not. I'll take that back. It's not that it's like it's not like the namespace ID is randomly generated when you submit the data, right? You know a namespace ID before you like submit to it, right? You can't just like submit data to Celestia without picking a namespace, right? In reality, though, the namespaces aren't like just simple decimal numbers. There's a format to them, right? I believe it's like a hexadecimal up to, I believe, 10 or 12 digits, if I recall correctly. And there's some other nuances where there's a couple of like reserved namespaces that are used for like for specific like consensus stuff and also like core applications. Like Celestia is ultimately a blockchain that does a little bit more than just like encoding data and making blocks, right? There's other modules, and because we use Cosmos SDK, so there are other modules and utility that Celestia provides to make this data like useful. And I believe, don't quote me on this, but some, if not most of the modules have like a reserved namespace for certain actions. And the namespace IDs that are these like hexadecimal numbers have like a prefix and like a sort of like identifier to tell the node software what kind of namespace ID is this, and then the rest of the hexadecimal number does signify like the actual identifier. I hope that like answered the question.
Yeah, thanks.
But yeah, I mean, if anyone has any other questions, please let me know. I can move around my slides and clarify anything. If I didn't like make something clear, or if some of this was like maybe too much, I can go over it again.
Yeah, there's a question about how to get more insights of namespace Merkle tree. I've been in the chat.
Okay. Yeah, sorry about that. I can't read the chat because like since I'm sharing the slides on my phone, and I'm like sharing my full screen on my phone, like I mean I technically can read the chat, but I would then like show the meeting again, and I can go back on that. But so the question is like how to get more like where can they read more about namespace Merkle trees? Is that the question? Let me see if I can. Oh, it actually doesn't let me see the chat. Interesting.
Yeah, I can read again. So any docs to get more insights about namespace Merkle tree?
Yes, so the Celestia documentation, if you go to docs.celestia.org, and you look up learn, like docs.celestia.org/learn, it will take you to an overview of Celestia. And inside of the data availability layer section, there's a subsection for namespace Merkle trees where this picture is from. But that section is it's essentially what I just mentioned. It goes over like like a basic overview of like what's a namespace Merkle tree. The like full robust definition of a namespace Merkle tree can be found on the Lazy Ledger paper. So that's the first point all the way at the top. The link, if you type that on your browser, should allow you to look at the PDF for the paper. And the specific part of namespace Merkle trees is section 5.2, storage nodes and namespace Merkle tree, where Mustafa defines like what is a namespace Merkle tree, like what are the rules, what is a hashing algorithm. It's not like super complex. Even though the diagram in the docs tends to have that effect on me and other people, where it's like you don't know exactly what you're looking at first. But when you think about it, it's a special type of Merkle tree, right? Ultimately, it's not it's not like one-to-one, say, with something like the Merkle Patricia tree from Ethereum. But obviously it shares like they're both of them ultimately are Merkle trees, so they share like similarities. And yeah, the namespace Merkle tree is more of like it's more important for the part of like how do storage nodes on Celestia store the data, and how you verify, right, like inclusion of the data into this like namespace Merkle tree. But they're not. I would say they're not that. I'm not going to say they're not important, but it's if you want to learn more about other aspects of Celestia, like the aspects that people usually talk about, right, like data availability, sampling, and whatnot. The rest of the paper goes over all of that. Because to be fair, namespace Merkle trees are only part of like a subsection of the original paper. Like it's only section 5.2 of the paper, and the rest of the paper goes over like block validity rules, fraud proofs, Solomon two-dimensional Solomon read encoding, threat models, data availability sampling, etc. But yeah.
Great. any other questions?
See if I can. I think now that I'm not sharing my screen, I can check the chat.
Yeah, any other questions? Okay, cool. So seems like no one have more questions, then yeah, thanks everyone for joining our session today, and thanks Diego for sharing. Yeah, and
Yeah, absolutely.
Yeah, thanks very much. Yeah, we'll see you next time. Yeah, thanks everyone.
Thank you.
Thank you.